either staying from the last session or coming in fresh for this one. Pretty excited about this session in general. What we are talking about is a study that was commissioned by the city of Cincinnati to explore kind of the market viability and technical feasibility of geo-exchange systems for the city. That was commissioned as part of the Municipal Investment Fund grant that has funded several other initiatives happening concurrently throughout the month of April. We are set to release this report towards the end of this week. So this presentation is really to summarize those findings and share that with the public. So yes, if you would like further reading after this, come talk to me. We have a 75, 80 plus page document you can really do a deep dive into. So lots of fun. Next slide, please. Maybe. Okay, so today's presenters, I'm Wyatt Ross, I'm building performance engineer with CMTA. We also have Dave Cook and Isabella Von Trapp from Geosyntec who will be co-presenting. And then Nikki Vandervoort has been the project lead on this from the city of Cincinnati. Nikki, I don't know if you want to say anything or just say hi. Great. Yeah, so this has been a great collaboration with the city, a really exciting initiative. So we'll talk about kind of our findings and then hopefully some potential next steps as well. Next slide. So I'm with CMTA Engineering. Again, we are an MIF engineering consulting firm, but we have been doing geothermal systems at building and district scales for 30 plus years before my time. Over almost 7,000 miles of pipe installed, projects all over the country, and over 200,000 tons of decarbonized HVAC through geothermal applications. This is the first geothermal U.S. hospital, but we've had a few other geothermal geo-exchange firsts in terms of building typologies. So overall, just a lot of experience with this topic. Next slide. You want me to cover it or you want to jump in, Dave? All right, we'll let Dave cover this one.
We didn't plan that very well, but hi, everyone. Dave Cook, Senior Principal Geologist with Geosyntec. Quick intro. Isabella, my colleague, and I came from Seattle. That's where we live and work, but I'm an Ohio guy. I grew up in Worcester, and I went to Wittenberg for my undergrad studies in geology, and then went west. So it's really nice to be back. But our firm, we've been focused now on, one of our practice group is on ground source heat pump consulting, geo-exchange. It's also known as geothermal heat pumps. So there's a lot of different terminology related to it. Today, we're just going to call it geo-exchange. The other way that geothermal gets confused is there's geothermal energy production. That's not what we're talking about today, and we'll talk more about the lower temperature, shallower geo-exchange. But we've done, we're earth and water scientists and engineers. We've done thousands of water well designs and installations. We're focused on ground source heat pump projects throughout the US and the UK. And one of our unique projects is in Washington State that we can talk about later, which this thermal energy model and thermal model is shown in the graphic there is related to a open loop system that we designed at a laboratory. Thanks, y'all.
Thank you. Next slide, please, Emma. So today what we're going to cover, we're going to start broadly speaking about kind of the impetus of this study and why geo-exchange is potentially a viable and important solution for the city and then the residents within. We're going to talk about a little bit kind of what Dave was building on there, what it actually is, and maybe more importantly, what it's not, because there is a lot of this verbiage is used interchangeably. It can be a little bit confusing, so we'll hope to clarify that. Then we're going to dive into Cincinnati's geology, pretty fun, and then look at the building level opportunities, some of the district energy system opportunities, and really the potential next steps or pilot opportunities that could follow from the findings of this report. Next slide. All right, so why geo-exchange in Cincinnati? So if you go to the next slide, there's kind of three main forces. There's more, but there's three big ones that are kind of converging to really incentivize exploration around geo-exchange systems. The first of those is the Green Cincinnati plan. So If you're not familiar, this was revamped in 2023, but has been going on for a long time, being updated in 5-year cycles. The emissions targets, they're kind of outlined for the city within that plan, is a 50% reduction by 2030 in terms of emissions, and then carbon neutrality by 2050. So it's kind of setting a timeline for finding technologies that can help the city reach those decarbonization goals. A second big focus is on reducing energy burden. So we'll talk a little bit more about this, but there's a significant portion of the city in our communities that are considered low income and disadvantaged communities that pay a disproportionate amount of their annual income is being put towards paying for utility bills. And so how can we help alleviate and address some of those concerns? And the third, what you heard in the last presentation, we'll speak a little bit more about during this, is the availability of some federal incentives specifically for geo-exchange applications that are available through 2032. So kind of pushing for some near-term investigations into this technology. Next slide. So on the Green Cincinnati plan, again, trying to reduce emissions as much as possible. I think it's important to note that buildings represent about 66% of those total emissions. And so when we think about how do we impact or affect these particular emissions, because HVAC energy use is one of the biggest components of building energy and building emissions, geo-exchange and its ability to affect both heating and cooling applications and domestic hot water needs is really one of the biggest levers available for us to start to address this huge tranche of emissions within the total emissions portfolio. Next slide. The other critical facet of this is that because the timeline for decarbonization is really looking at 2050, when we think about major heating and cooling infrastructure, there's typically an equipment lifespan somewhere in the 15 up to 25-year time horizon. And so we are currently in the equipment and infrastructure replacement cycle where we have to start addressing these systems if by 2050 these buildings are going to be decarbonized. If we miss a replacement cycle that happens next year or the one that happens in 5 years, there may not be an opportune time to then address the decarbonization and replacement options and opportunities until the next replacement cycle, which is going to happen after 2050. And so again, if geo-exchange is viable, it is, then we want to make sure that we are putting everything that we can towards addressing and capturing those near-term replacement cycles. Next slide. So this map, kind of transitioning to the energy burden and LIDAC communities, this map kind of highlights in orange where those particular neighborhoods and communities are. There's a lot of pieces and parts to the definition of a LIDAC community that can determine how that actually is, whether or not it is true that it is considered a LIDAC community. Those can be everything from environmental conditions to actual poverty metrics. But the general consensus is that these are low-income or disadvantaged communities that are suffering more so than other neighborhoods from energy burden. So if you go to the next slide, what that actually means, energy burden is typically qualified as communities or households that are spending more than 6% of their annual income on utility costs. So there was a study done for the city of Cincinnati, found that the median energy burden is around 4.75%. But when you adjust that for low-income households, it actually switches to 9.16, almost 10%. And if you look at this chart, you can see there are several communities that are well above 15% of household income going towards utility costs. And so what that means is, and for the city's priorities, is figuring out how can we not only address the decarbonization goals, but also find solutions that help lower utility costs and energy burden for our communities. Next slide. So again, some of this was covered in the last presentation, but I do think it helps to set the stage. Kind of the main point of this is over the last year or so, we've seen utility costs rise by 30+%. PJM's capacity markets are ballooning. If you're kind of tracking what's going on in the broader energy community or energy news. And so what this means is that this energy burden problem is not necessarily going to get better on its own. Utility prices are rising. And so we want to find solutions that can help address those concerns while also doing things like reduce emissions, improve indoor air quality, etc. Next slide. The final piece that's really driving this, again, is the investment tax credit. So these are federal incentives that originally came into play through the Inflation Reduction Act. For geo-exchange systems, they've been modified, but left and continued as part of the One Big Beautiful Bill. And these are significant because they allow projects that are doing geo-exchange systems to potentially get a tax credit or a direct payment, whether you're a private or nonprofit entity, of up to 30 or 70% of the entire geo-exchange system. So it's not just the well field, which we'll talk about in a minute, but it's also the building level components, all of your HVAC equipment that's interconnected to that well field, any controls that are interconnected to that well field, domestic hot water that's interconnected to that well field, piping, ducts, you name it. And so this is a real generational level incentive for addressing both existing systems and their conversion to geo-exchange, but also helping to finance new systems altogether. So you can see the kind of the buildings that are potentially applicable, that is applicable to. This really goes into the credit stack on the next slide. And so there's a 30% base credit if certain prevailing wage and apprenticeship requirements are met, or if there's capacity exceptions. But generally speaking, there's going to be a 30% base credit and then 10% bonus to 20% bonus incentives depending on certain criteria. One of those is domestic content, which is a fairly achievable percentage of domestic material for geothermal systems, so that's pretty readily accessible. The second piece there is a 10% adder if you're located in an energy community, so that is just purely geographical, so where the project is going. One of the things that can qualify you for that is if you are installed in a brownfield, so we'll talk a little bit about that. And then the last piece there is for low income or tribal communities. This is more of a competitively awarded bonus adder, and it is also geographically limited. So something that could apply, but doesn't necessarily universally apply. So all in all, you're talking 50, potentially 70% of total project costs, everything interconnected to geo-exchange could potentially be covered by this tax credit. Very important to note that this is, traditionally only for-profit taxable entities could leverage this. Important to note that because this applies to non-taxable entities as well, municipal governments, nonprofits, public schools, public institutions, all of those non-traditionally eligible entities can leverage this tax credit. Next slide. So overall, the driving question for this study and kind of the purpose that it's trying to address throughout is geo-exchange district heating and cooling or building level applications a viable solution for, one, addressing the city's decarbonization goals, but also helping to address some of the equity concerns and benefiting the community at large. Next slide. And with that, buried the lead a little bit, but we'll then transition into actually what is geo-exchange? What are we actually talking about in terms of technology and application? Dave.
Okay, the answer is yes. Oh gosh, I spilled all the beans already. Isabella will explain why the answer is yes for geo-exchange for Cincinnati. Let's go to the next slide. Hopefully everyone has heard of geo-exchange, geothermal heat pumps. It's simply just extracting the heat energy that's in the shallow surface of the earth and using that to heat buildings. And then you just reverse the cycle with the heat pump and you collect the heat in the buildings and you push it back down in the ground. And so you either do that through some pipes or in the soil or rock, or you do it through water extraction from an aquifer. So let's go to the next slide. And this is just a graphic of the three primary types. You've probably heard of a closed loop system, which is where you drill boreholes down 300 to 500 feet deep into soil or rock, and you put in a U-bend loop and you grout that loop. It's about an inch diameter HDPE piping. It gets networked and headered together in a system and then back to the mechanical room. You run a cold fluid down through that HDPE piping and you move heat from the surrounding earth into that fluid, raise the temperature of the fluid, take that back to the heat pump and use that advantage now to distribute heat out to the building. Do the same thing in that closed loop system. You collect the heat in the building, run it through the heat pump, push the temperature up, push the higher temperature back in that fluid into the ground, and then the heat moves out into the earth. The second graphic is a supply and return well system. And this is very similar to a water supply system. And it's not routinely used around the U.S., which is really interesting to me as a geologist, hydrogeologist, because these are really high. When you have an aquifer present, they're really highly efficient, more so than a closed loop system. And we need to think about this more. And you'll learn more about this in a minute when Isabella, my colleague, talks about Cincinnati. But you pull water out of the aquifer, run it through the heat pump. The typical temperatures of the ground in the Cincinnati area are around 55 to 58 degrees Fahrenheit. That's in the surrounding rock and soil. Same thing on the accessible aquifer, shallow aquifer here in the Cincinnati area. This third one you might not have heard about. This is pretty new technology out of the University of Minnesota. And it's being pioneered in the state of Minnesota, primarily around Minneapolis, St. Paul. And there's a group there that has designed an in-well heat exchanger. So you've got your heat exchanger down in the aquifer, and they've designed a system to move aquifer water, groundwater, across the heat exchanger. Then that heat exchange is delivered up to the heat pump building. And there are benefits to each one of these technologies. Go to the next slide. These are just some of the pictures of the installation of different types of ground source systems. Drilling rig, that's how these systems are installed, both closed loop system or installation of a groundwater well, supply and return wells. The outcome in the lower left corner is what an open loop well system looks like. So you have a few of these stick-up wells that can be accessed at the surface. So once they're installed, they're very low. They're very low in the area that they cover on the ground. A closed loop system is a big bore field, so you've got to dedicate a lot of land to a closed loop system. And you can see they're installing a closed loop system in that, all the other pictures there. Okay, next slide. For those of you that are designers, this is the way that we evaluate different types of systems against one another, which is the coefficient of performance. The way I like to think about it is look at the second row there of electrical resistance. You take 1 unit of electricity in, and it produces 1 unit heat out. That's the baseline electrical resistance heating, and we compare everything to that base. A 1-to-1 ratio. Air source heat pumps have a 2.5 to 3 times benefit over electric heating, and ground source heat pump 4 to 5 times more efficient heating. When you start to do a district energy system, that coefficient of performance goes up even higher, more efficient. Now we're sharing surface and tapping the ground loop when needed. Next slide. And this is my wrap-up slide. So the key things about geo-exchange. There are 5 categories, examples here of where best to use geo-exchange. They'll work in any one of those categories, but if you can layer any of these together on top of one another, it just becomes even more effective and efficient. So new building construction, that's a great place to think about and deploy a ground source system. You can, if you're building a new building and you're predicting that energy prices are going up, there you've layered 1 and 2 together. Very effective, efficient. You think about geo-exchange. We've heard a lot today, both in the prior talk and Wyatt just described it. Tax credits, tax eligible for a lot of users or renovators. And then the rest of this talk, we're really going to focus on balance sheet cooling loads at a district level scale. That's where things get really exciting for us, designers and for jurisdictions. Then we've talked about decarbonization goal related to geo-exchange because you're switching to electric pump system and electric pumps opposed to carbon-based fuels buildings. So that's kind of the overview, the basics of geo-exchange. I'm going to turn it over to my colleague Isabella to talk about probably a lot more exciting stuff, the geology and hydrogeology of Cincinnati.
Hey everyone, my name is Isabella Von Trapp. I'm a senior hydrogeologist with Geosyntec, and I thought I'd give you a little geology lesson on Cincinnati. So next slide, please. All right, put yourself back in time. 450 million years ago, the whole Ohio area used to be a shallow tropical sea. It was warm, it was depositing mud and clay. Those sediments got buried, they eventually liquefied, which means they turned into rocks, and then they got uplifted. Fast forward, last 10 to 20,000 years, the Ice Age. There's a lot of glacial activity in this area, so we have these big glaciers moving back and forth and kind of carving some of that limestone and that hard rock that's at the surface from what used to be the shallow sea, and it left behind sand and gravel and these river channels, and they kind of formed what you know of Cincinnati today. So on the map on the right, that's a map of hydraulic conductivity. That just is a fancy word that means how easy can water move through rock. So if I were to overlay a geologic map on top of this, you would see that it aligns pretty well where there's really low hydraulic conductivity, or the purple color. That's where the limestone and that hard basement rock is exposed at the surface. And then where it's orange and yellow, that's where all the sediments that move water around are located. Next slide, please. So why does this matter? I think this slide really kind of underscores the importance of knowing about the geology before you plunge into a geo-exchange design. So you heard from Dave about closed loop systems. Closed loop doesn't take water from the ground. So you can really install them in any kind of geologic conditions. They're highly adaptable, which means you can put them in the Ordovician bedrock, even though there's no water that moves through it. Whereas an open loop system or an in-well heat exchanger really needs an aquifer to make that work. And Cincinnati is lucky because a big part of the city sits atop a really highly transmissive or high hydraulic conductivity sand and gravel aquifer that can move a lot of water. Next slide, please. So not very far from here, there's several wells that have been tested at about 1,000 gallons a minute. Just for scale or context, a single home on an individual well might need 5 to 10 gallons a minute for its water supply needs. So 1,000 is a lot. And that particular well only experienced 2 feet of water level drawdown. So the static water level, let's say it's 20 feet below ground surface naturally. And then when you turn the pump on, it goes down 2 feet. Pretty good. That tells me that you can actually pump it a lot harder than that because you have a lot of available water level or available drawdown in your well. So for the engineers in the audience, maybe you could pump it at 5,000 gallons a minute, which corresponds to a pretty significant heating and cooling load. Next slide, please. So already kind of talked about this, but I'll just reiterate here. Open loop systems and in-well heat exchange systems could work really well in Cincinnati because of all those really nice sand and gravel sediments. So this map is different, but it essentially conveys the same thing. This is a well yield map. So the lighter colors you'll see that correspond with where the sand and gravel is located is producing upwards of 1,000 gallons a minute, whereas the limestone and the hard rock that's exposed at the surface in the hills is low yielding, that darker purple color. So a couple of the areas that we've really kind of honed in on for this study are the Central Business District, Queensgate, if you follow that up north toward Reading, the East End, and then also there's a pocket near Oakley and Madisonville that was probably an ancestral river channel from when the glaciers were doing their thing, and left behind some nice sediments. Next slide, please. Okay, so I mentioned earlier, we know that closed loop systems can be installed pretty much anywhere. They're highly adaptable, but one of the challenges with them is they're expensive and they require a pretty large footprint. So you only get a really small amount of capacity per one borehole. So if you're trying to, let's just say, for example, heat and cool a system that needs 1,000 tons, you might need 500 boreholes. And if those are spaced 20 feet apart, we're looking at 4 acres. And in an urban setting, you don't always have 4 acres of green space that you can devote to a closed loop system. And that might cost on the order of about $6 million. Whereas, next slide, please. An open loop or an in-well heat exchange system, to get that same capacity, so apples to apples comparison, 1,000 tons, you might need 1 supply well and 1 return well in this kind of geologic condition. And that, you know, could be around $2 million. So don't take those numbers to the bank. Those are site specific and, you know, highly dependent on the geology, but I think it gives you a sense of scale. Typically that the aquifer based systems tend to scale a lot better in terms of costs. Oh yeah, and also if you're reading the slide, please note we caught this morning after it was too late. The blue is not the aquifer. It should say orange or yellow. Next slide, please. Okay, so just briefly should mention when you're installing either an open loop, closed loop, or in-well heat exchange system, there is some permitting that needs to be done. Registration with Ohio's Water Resources Department and UIC registration for return wells, but nothing insurmountable. I think there's some annual reporting that is associated with these, but there's really no structural barriers that make permitting these systems a challenge. Next slide, please. So I think this is my last slide, and I think just in summation, if you take anything away from my section of the presentation, note that while closed loop systems are technically feasible anywhere, they're not always the most favorable option just due to the cost and footprint requirements. Whereas a high yielding alluvium system like you're lucky to have here in Cincinnati is really amenable to open loop and in-well heat exchange systems, and those tend to scale really well in terms of costs. And all of them really are feasible and permittable, so congratulations. And I'll turn it back over to Wyatt. Thanks.
The irony is that we are in a bank for those numbers. So I am going to cover the building level opportunities in addition to district systems. So we'll kind of go through what this looks like in terms of opportunity for the city. So you go to the next slide. In general, what we found and what you'll find in the report is we looked at several building typologies and tried to understand in terms of impact, what kind of energy cost savings and energy reduction and emissions reduction performance could we achieve with geo-exchange systems. And so when we look at legacy equipment and industry benchmarks for how buildings perform typically, and then overlay on top of that how they could perform with geo-exchange systems applied, in general, what we found is that within HVAC energy consumption, these buildings could achieve 56 to 67% energy reduction. So a very significant reduction in total energy use. Next slide. And again, same way that closed loop systems are highly applicable or generally applicable, in general, geo-exchange does not preclude itself from being applicable to any one particular building typology. It is fairly universal. And so these are examples of buildings in a range of applications that all have geo-exchange systems installed, ranging from commercial office to municipal facilities, healthcare, educational facilities, hospitals, residential, etc. And so in the report, we kind of go into a deep dive of what this might look like in terms of actual systems. Yes, yeah, a few good examples. Next slide. And so the reason that this is important is because when we think about, again, where does energy consumption occur in our buildings? If we just look at all buildings and all of the end uses across the US, generally what you see is that heating, cooling, ventilation, conditioning, domestic hot water represent well over 50% of annual energy use in buildings. And those are all systems that geo-exchange can impact. And so if we can get 56, 60% energy savings across all of those categories, across 50+% of our building's energy use, tremendous opportunity to reduce energy consumption, reduce operating costs, and drive emissions reduction. Next slide. And so we're not going to go into a ton of deep dives on the building side in terms of applications, but just wanted to highlight a few somewhat case studies to prove the point that this is certainly achievable. So these are examples of real K through 12 schools in the same district as an example. And you can see the systems that don't have geo-exchange or geothermal heat pumps versus the ones that do. And the metric at the bottom is energy use intensity. So again, kind of the miles per gallon of energy use for buildings, how much energy per square foot they're consuming. And lo and behold, the ones that have geo-exchange are consuming roughly 50-ish% compared to their peers. There's a great local example, Bowling Green High School, north of Cincinnati, obviously, in Ohio, but a good testimonial from the superintendent there, just talking about the potential energy savings up to $25 million over 50 years that's expected to save that school district. There's a lot of great research from Undaunted K-12 and other nonprofits that have really looked at K-12 applications for geo-exchange systems to reduce operating costs and drive revenue back into the school's operating budgets. Next slide. So this is, again, just kind of exploring a similar elementary school example. So this is a life cycle cost analysis looking at baseline code minimum HVAC systems. So in this particular case, it was fan coil units served by an air-cooled chiller and a gas-fired condensing boiler. And it was expected over, I think, the 25-year lifespan, maybe 30-year, I can't remember, to cost around $12.9 million. When we originally explored a geo-exchange system as an alternative, if you go to the next slide, originally what that project saw was roughly a 6-year payback. Again, doing things like right-sizing the system. When we then factor in what is now achievable through the investment tax credits and the direct payments through the federal incentives available, in this particular case, if you jump to the next slide, we saw this be less than a 1-year payback. So essentially, once that project went into operation, they were able to receive, I believe in this case, 40% of the total HVAC line item back in terms of a direct payment, and that immediately offset the cost of the initial increase for installing the well field, and then allowed for additional priorities for the project to actually be paid for. Next slide. So again, another example, it's not just institutional or higher education or K-12 buildings, office buildings are another great example, clearly in Cincinnati, especially in the downtown. That's a huge important building typology. Again, when we think about general energy use in traditional commercial office buildings, about 53% of the energy use is driven by heating and cooling. Another 3% roughly for domestic hot water. So you have 56% of total energy use in a typical office building that can be directly impacted by geo-exchange systems. And so if you look at the next slide, this is not downtown, but in Laughlin, Ohio, there's a great example of a historic retrofit that used geo-exchange to take a 100-year-old office building and make it a net zero energy building. Cut the EUI from the baseline of I think 85 EUI down to a 30 EUI, so a 65-ish% reduction. And again, a lot of that is because you are impacting 56% of the building's energy use by using these highly efficient geo-exchange systems, as Dave pointed out, could be up to 5 times more efficient than your legacy equipment. Next slide. Same thing can be proven out in residential applications. So this is a study that was done looking at, by the Rocky Mountain Institute, looking at kind of upper Midwest utility companies. And so they looked at metric tons of CO2 reduction for different HVAC systems. So again, emissions reduction. And they also looked at operating costs. And so this would essentially translate to utility costs across single family homes. The dark blue in each of those charts represents ground source heat pumps. And so you can see not only does it achieve the greatest amount of emissions reduction in those utility grids, it also achieves the greatest reduction in operating costs. So again, kind of regardless of building typology, a lot of merit to ground source heat pumps. Next slide. And so on building applications, I think kind of the last thing that I want to leave you with, because I think it is tremendously important when we think about those replacement cycles that we discussed in the beginning and kind of this opportunity window for aligning current infrastructure renewal with the 2050 targets that Cincinnati has. The ITC is really a generational opportunity to get a significant portion of infrastructure renewal covered by a federal incentive. And so, oftentimes you will see that we have a $1 trillion problem in the US in general, where there's a tremendous amount of deferred maintenance in our existing building stock, especially in our legacy HVAC systems. So we have steam piping infrastructure that needs replaced, water infrastructure that needs replaced. We have a ton of equipment in our buildings that is ready to be renewed. Because the ITC applies not only to the well fields, but also to the equipment itself, this is a great opportunity if you're planning capital investments, leverage these funds to help achieve a more efficient and decarbonized replacement HVAC system. Next slide. So high level, kind of the design considerations that we think about, especially when you're looking at this at a building scale, an individual project. In general, when you're thinking about trying to keep these project costs down, you've heard some Dave and Isabella talking about how, in particular, closed loop systems can get very large and very expensive. If you want to keep those costs manageable, you definitely don't want to be using rules of thumb when it comes to design, right? You want to be detailed, right-sizing our systems. We want to make sure that we're doing everything we can to really study the local geology, and having the data set that's part of this report is really important, so that we understand what the conductivity of the ground is, what are the flow rates that we can achieve, and how do we right-size our systems so that we're not throwing money away at oversized systems. The other big piece of geo-exchange systems is balancing loads. And so the simplest way to think about this is if you only need heating for your building, you're over time going to pull a lot of heat out of the ground. And especially in closed loop systems, that imbalance will require you to size a larger well field. Same thing would be true if you were thinking about cooling only applications. The more balanced your loads are on a system, the more balanced heating and cooling demand is, the less heat exchanger, or the smaller the system you actually need installed in the ground. And so that's why district systems make a lot of sense, as Dave was alluding to, because you do get a lot of balanced load across multiple building types. But in particular, in your own building, kind of going back to the previous presentation, thinking about how the loads in your buildings are designed and optimized to reduce heating, cooling, and balance those goes a long way to reducing the upfront costs of your ground source heat exchanger. Last thing, obviously it's very important anytime you're digging, you want to coordinate with your local utilities, coordinate with local site elements, and really partner with local drillers. We have a really good ecosystem and a business ecosystem of drillers in the region that have a lot of experience that can be great partners in design and implementation. Next slide. Okay, so district systems. So I'm excited about this piece. If you jump to the next slide, when it comes to district systems, really what differentiates this from building level applications is really just the number of buildings that you're talking about interconnecting onto one geo-exchange system. So a lot of times you will hear district thermal energy networks, district systems described as thermal energy networks. It's not necessarily too different in concept from distributing chilled water, distributing hot water or steam. But in the case of a geo-exchange application, you are distributing an ambient loop or a neutral temperature loop with water or a fluid, essentially the same temperature as the ground. And then each individual building pulls off their respective heating and cooling needs from that loop. Next slide. And so part of our analysis, one of the things that we looked at was a peer city review, looking at precedent district energy systems that could be applicable or provide some lessons learned to the city. The three that we looked at were Denver, Colorado, we looked at Rochester, Minnesota, and we also looked at Framingham, Massachusetts. And each of these, have a lot of lessons learned, but I think each of them offer kind of three unique, valuable lessons that the city in particular can glean from. Next slide. So the city of Denver, this is actually one that is not a developed system, but it's one that has been studied. And there's kind of two driving factors on why we think this is important to incorporate some lessons learned from. The big one is that the impetus for this study that Denver did is driven by two parts. The first is they have aging infrastructure. So they've got an existing steam and chilled water system that needs to be replaced. The second is they have a local building ordinance that requires buildings to become more energy efficient over time or they get fined. And so they commissioned this study and the findings of the study because they wanted to understand how a potential thermal energy network and a geo-exchange system could help them both meet their building performance standards while also reducing costs for building owners in the city. And so what they found is if they converted the existing chilled water system to a district energy system, they could actually help achieve electrification across the city at 30% of the total cost if each individual building was to do that by themselves. So tremendous energy cost or capital cost savings across the board by implementing this. They were also able to make an alternative compliance pathway for compliance with that building performance standard. So rather than just making buildings reduce their energy consumption, they can also comply and avoid those fines by interconnecting to this future potential district geo-exchange system. So that does one of two things. It helps drive market demand. Again, make this more of a viable solution. Next slide. So this is an example of what they're currently considering. High level, essentially what they're looking at is decommissioning the steam plant or potentially decarbonizing that through an alternative means and leaving that as an alternative option. But then they're looking at repurposing the existing chilled water system and converting that into a district ambient loop. So rather than a series of hot water and chilled water pipes going throughout the entire city, you would just have a single pipe with neutral water temperatures circulating through every building. And then at the building level, each individual building would have its own water source heat pumps or respective equipment to access that neutral loop and provide heating and cooling within the building. One of the benefits of that is it gives owners of buildings a lot of flexibility. Also, because you're switching to a single pipe system, you're reducing a lot of the capital cost of running this new infrastructure through a big urban region. Next slide. Rochester, Minnesota, this is another example. Again, really great lessons learned for the city of Cincinnati, simply because of the hydrogeology similarities. And so in this particular case, Rochester sits over top a similar aquifer to what the city of Cincinnati sits on, at least in the downtown core that Isabella explored or explained. And so what they did is they created a multi-part pilot study. The first phase, they interconnected their city hall to a in-well heat exchanger system that, again, kind of single bore, sits inside the aquifer and does heat exchange with that aquifer without actually removing or extracting any water from the aquifer. That pilot was successful and proved out both the financial viability and the technical viability or feasibility to extend that system into the broader downtown core. And so they implemented what I believe is called the downtown building energy transition. Don't quote me on that. But this connected, I believe, 5 additional buildings, the Mayo Civic Center, a public library, a theater, and several other large facilities in the city's downtown. They installed only 5 additional wells, and they were able to achieve all the capacity they need. And I believe that system went into effect and is actually operational as of last year. I believe it's saving $900,000 per year in energy cost savings. And it's achieved something like 75% of energy use. So again, a really interesting application simply by the effectiveness and kind of a proof case, but also because of the hydrogeology similarities. Next slide. This is a diagram, won't get in the weeds, but the core of this is those 5 wells that you see in purple. That was all that was needed to supply all of these buildings. Again, because this is an in-well system leveraging the aquifer. So rather than having a really land-intensive closed loop system, they were able to minimize that and use more of an aquifer-based system. Next slide. Last one here in terms of precedent, Framingham, Massachusetts is an interesting case study just because it was the first utility owned and operated and implemented geo-exchange system in the US. So in this case, there's 30 plus buildings that are going to be interconnected into this system. This is more of a traditional closed loop application with well fields distributed across that entire network. Really, the application to Cincinnati that's interesting here is because this is a utility-owned system. All of the capital costs were borne by the utility company. And so all of the residential buildings that are interconnecting to this, they don't have to front any of the money to interconnect to that system. This just becomes a line item, the same way you would purchase natural gas or purchase electricity. They are now purchasing thermal energy off this district system. So the utility is recouping the costs, obviously, of their investment from the utility prices, but the customers are still expected to see a 20% reduction on their annual utility costs relative to what they were paying for gas and electricity. So this is kind of an interesting model in terms of, in particular for residential building owners, how can they access geothermal and avoid some of the prohibitive capital costs that typically are a barrier for smaller building owners. Next slide. Okay, and so that brings us to then what we studied in terms of district or candidate districts in Cincinnati. And again, I would just say that the goal with this analysis was really to understand the opportunity. It's not intended to be exhaustive, as if these are the only potential locations for district systems across the city. But what we were hoping to do by capturing the downtown, central business district, as well as what we're calling the Over the Rhine district, but which captures parts of Pendleton and even into the West End, is to really capture cast a broad net in terms of the building types that we were capturing. So we wanted to capture the downtown core, as well as kind of the historical fabric and some of the 19th century or Italianate architecture that you see in over the Rhine. Also capturing kind of the commercial end versus what is more of a residential application. I will just note we did look at a third district, which was kind of in the UC medical corridor in Uptown. Ultimately, that was excluded just because we couldn't get enough data to make that a real viable study, but that's something worth considering in a future phase. Next slide. Okay, so downtown, kind of the important thing to note here is essentially the way that this study was done, and this was performed by our good friends at Go Sustainable Energy. But what was done to perform this analysis is utility data was used from all of the parcels that you see highlighted in green. And then any parcel highlighted in red was then estimated. And what was done is we were able to use a regression-based analysis to go from the annual energy use of these buildings in terms of electricity and natural gas, and then back into estimates for how much of that energy is actually allocated to heating and cooling. And then based on kind of traditional existing HVAC equipment and those efficiencies versus geo-exchange, estimate the potential savings in terms of emissions reduction, heating and cooling energy, electricity, and natural gas savings, as well as operational cost savings. Next slide. And so what you'll note, obviously the downtown district represents a large majority of these facilities are high-rise or large commercial facilities. And so one thing I just want to note on this analysis is that it is likely very conservative because of the nature of the regression analysis that was done. A lot of the loads in a commercial building like this aren't necessarily weather dependent. You know, there's a lot of people, there's a lot of equipment. So heating and cooling isn't just driven by the weather outside, but also the use of the building. And so those heating and cooling needs are probably underestimated in this analysis. And so everything stated here is probably highly conservative. So this is probably a floor rather than a ceiling in terms of potential opportunity. But what was found across the board, and I'll kind of just focus on the bottom section there, is similar to what we saw in the individual buildings. Geo-exchange could represent up to 67% reduction in heating and cooling energy consumption. That translates to a 50% reduction in CO2 emissions because you're eliminating a significant amount of natural gas combustion, which is essentially the equivalent of taking over 5,000 cars off the road every year. $4.1 million in annual energy cost savings. And kind of what's most interesting about this, for the massive amount of a heating and cooling demand that is represented by this district, because of the conductivity and the amount of flow that we can receive or see through the aquifer underneath this portion of the city, if an in-well or open loop geo-exchange system was implemented, it's only estimated that this system would only take 20 to 40 wells to actually cover the heating and cooling demand, which maybe seems like a lot, but compared to a closed loop system, that is hardly anything. And so that's just a really interesting takeaway for such a large amount of building interconnection. Next slide. So similarly, again, kind of splitting these two pieces apart, the second district we looked at was over the Rhine. Not just over the Rhine. Again, there's Pendleton, some of the West End incorporated in there as well. Very similar. What you see in green are the utility bills that we had for those parcels. What we had in red was estimated. But what we essentially did, same process, backed into estimates for annual heating and cooling energy use, and then estimated what the savings would be. Compared to the downtown district, obviously this consists of more of a residential, multifamily, and mixed use building typologies. You're looking at more mid to low-rise residential and multifamily, obviously some commercial end use as well. Next slide. So very similarly, one of the things that we found in terms of annual energy reduction, 68% reduction in heating and cooling demand, kind of like a recurring theme there. 49% reduction in CO2 emissions, $1.9 million per year in annual utility cost savings. And again, for such a large area, because this also sits over top of the aquifer, only 7 to 16 wells likely estimated to be needed to serve all of that building interconnection. Next slide. Actually, go back one slide. Just one point I wanted to mention. Both of those districts, one of the key findings in both cases, we found that there was a 1.1 to 1.3 ratio in heating demand to cooling demand. And the reason that's important is it essentially just tells us that the heating and cooling loads are very balanced, which is really what you would expect for our region. We have a mixed, fairly balanced climate. But what that means is if all of these buildings were interconnected, you would see those highly balanced loads that we were talking about that are extremely beneficial to district systems because it allows you to drastically reduce the total capacity you need to install, making the first cost more favorable. All right, next slide. So in terms of potential next steps, there's really two kind of core pilot projects that we explored. Go to the next slide. We do think it would be beneficial to have at least some pilot project focused on, in particular, the aquifer-based systems of the city. So there's a lot of precedent across the city on traditional closed-loop systems, both in the city proper and in the immediate greater Cincinnati area. But in terms of a pilot project's benefits, the ability to help de-risk and shine more information. Again, this is kind of more of desktop research building on some really significant data sets that are made available by the state of Ohio, but no actual wells were drilled as part of this analysis. And so having pilot projects that can help really pull a test well, understand flow rates, understand aquifer productivity, all of those things would go a long way to really solidifying the true opportunity here. Next slide. And so in our report, we essentially provide two recommendations for consideration, certainly not exhaustive in terms of the pilot projects that could be implemented. The first recommendation model would be similar to the Rochester, Minnesota model. So in this case, it would be some municipal building taking the first step to look at either a full or partial conversion to a geo-exchange system, leveraging an aquifer-based approach, so whether open loop or in-well heat exchanger. We've highlighted a few examples, the City Hall, the library, Hamilton County Courthouse. Really could be any number of buildings. It could be smaller scale, police, fire stations. There's obviously great precedent from other municipal buildings that have done closed loop in the past. But the idea here is really taking that first step to understand how an aquifer-based system would perform. And then this could be either the first leg or kind of the first phase of a broader district system explored in the future. Next slide. The second recommendation that we gave in the study, while we did study more of OTR in terms of the candidate district, the West End actually poses a pretty interesting opportunity in terms of the district system just by the nature of the buildings included. And so with the city's focus on LIDAC communities and energy burden, and with the higher percentage of energy burden experienced in the West End, this could be a great candidate. A couple of things that help drive this as a potential pilot. One, there's a great mixed use of building typologies, everything from affordable housing to civic centers to commercial applications, K through 12. There's also a decent amount of green space that's available. So you have several recreational areas, Queensgate Recreation Area, L'Oreal Recreation Area. I think there's a couple more. So there's a more availability as compared to downtown in terms of locations where drilling could occur. And those affordable housing units, there's been consideration of large scale upgrades happening in those communities. And so there could be opportunity to implement this alongside some of those capital projects to help maximize some of the effectiveness. And then there's also just the proximity to downtown. So this isn't something that necessarily would have to be done separate from a future expansion because they are proximal to each other and you're in that great aquifer productivity zone. You could even expand this system to capture more of the downtown core at a future date. Next slide. So overall, I mean, kind of the key takeaways here, hopefully it's obvious at this point. First, the geology in general across Cincinnati is really favorable to geo-exchange. So closed loop, generally an opportunity everywhere. There's gonna be places that are more effective than others, but that's generally going to always be an option. In those downtown building district or downtown business district, East Side, Madisonville, Oakley, great opportunities for open loop and in-well heat exchanger systems. There's a lot of precedent on what this could look like. And so building off of this Pure City research, building off of numerous case studies for various types of geo-exchange systems, there's a lot of lessons learned and best practices that have been established already. The financing stack really works out, especially right now with the incentives from at the federal level. So the ability to leverage those, the efficiencies and cost reduction just from operational costs, all of those things work together to help make this a very financeable strategy. And then the last piece is just kind of the policy and the near-term advantages. So with the 2030 commitment or goals through the Green Cincinnati plan, as well as the 2050 targets, paired with the sunsetting incentives at the federal level in 2032, really pushes for near-term investment and makes that kind of a priority. So all of those really work together to make geo-exchange a very viable and near-term solution for Cincinnati. Next slide. And we did it. So with that, I will, I think we have some time for questions, correct? Okay. So maybe I'll take a few questions if anyone has some. I know it's towards the end of the day. Yeah, Chad. Yeah. So the question was regarding open loop systems, is there increased maintenance? Is that prohibitive compared to a closed loop system? I think the answer is potentially yes. Certainly there's more maintenance in an open loop system than a closed loop system, but what can really drive that to be excessive maintenance is relative to water quality. So anecdotally and in past experience, what you'll see is we have high mineral content in our water in the city of Cincinnati. And so if you were doing an open loop system where you are pumping water out of the aquifer, for example, depressurizing it, running through a heat exchanger, a lot of that mineral content can separate from the water and then foul up heat exchangers and create increased maintenance. I would say that is certainly possible and there's room for exploration there, but there are also design considerations and design strategies that can be implemented to help reduce some of those effects. So keeping that water under pressure, minimizing its contact with air are all things that you can do to help keep all of that mineral content entrained in the water so it doesn't separate and help eliminate a lot of that fouling. I will say that is why the in-well heat exchanger applications could make a lot of sense because the heat exchanger is just in the aquifer. You're not actually bringing that water up to the surface level. You're avoiding the potential of depressurizing that, and you're avoiding those minerals separating from the water, and you avoid a lot of those fouling concerns. That's a great question. The question was, how long has the in-well technology been operational? In Minnesota, they've been doing it. I don't know what long time is relative, but probably a decade or more, I would guess, going on that. But it is a newer technology. So I know we have designed systems that are operational and we've had success with that are currently leveraging that. But I don't think it is something where we have 50 years of data necessarily. Is it closer to 5? Okay. Yep. Yeah, so I'll answer. Yeah. Yeah, so that's a great question. So I'll answer the first one, and I'll let Isabella answer the first question relative to the aquifer. So the second question was, what types of capacities can you get out of a typical well? What we see for a typical 300 to 400 foot well is roughly 2 to 3-ish tons per well in Cincinnati. That is a relative metric because it does really depend on the building loads, and it's not just a single number that's going to determine what capacity you get. It's really about how does that annual profile look in terms of how much heat you're exchanging, either pushing in or pulling out of that well. But a good rule of thumb, and again, don't use rule of thumbs, is roughly 2-ish to 3 tons per well. To give some context on in-well heat exchangers versus open loop heat exchangers, a single well there is upwards of 200 tons, or even more in some cases. And so tremendous more capacity per well than a closed loop versus in-well heat exchanger or aquifer system. The first question, and I think I have this right, was the water in our aquifer took a long time to get there. And so okay. Well, I think it is a valid question in terms of the charge of that aquifer and concerns about potentially depleting that or using that water. Maybe let Isabella address that in general.
So I think there probably are certainly aquifers in Ohio that are deeper and what we would consider confined, which means they're separated from the surface by a low permeability layer. And the confined aquifers tend to have older water that's worked its way into the aquifer from years and years of recharge. But in the Cincinnati area, we call this an unconfined aquifer, which means the water that rains down typically just infiltrates straight into the aquifer. So it gets plenty of recharge every year from just natural rain and runoff and things like that. And then in terms of the depletion, an open loop system is non-consumptive. So whatever you take out, you put right back in at the same quality and quantity. Really, the only thing that should be different is the temperature. So in that sense, there's not really any water depletion concerns or like regional lowering of the water table or anything like that.
I think Ollie, you had a question? Yeah. Yeah, so that's a great question. So the question is, if you do a district ambient loop, essentially how do buildings actually interconnect to that and what does that look like? And so one of the benefits of a what is called a 5th generation district energy system with that ambient loop is that it really provides a lot of flexibility on the owner side of how they want to interconnect. And so really traditional equipment can utilize the ambient loop. And so it wouldn't be a boiler. You would be leveraging heat pumps, but essentially they would be water source heat pumps in some configuration that would either be water to air. And so they would just directly connect to that ambient loop. That would be the heat source and heat sink. And then they would condition air that goes to the building. Or they could be water to water systems where they are pulling off of that ambient loop and then generating chilled water or hot water to distribute into the building. And so really on the building side, they're very conventional systems. A lot of times, typical large buildings, for example, are going to have chiller plants of some kind or large mechanical infrastructure. That really stays fairly consistent in terms of how that gets distributed into the building. What changes is how they get heat or reject heat, and that would just transition to being interconnected to the ambient loop. In terms of models for how that works, there is the question of who pays for that building level equipment. Under a kind of a traditional model, the building would pay for that equipment. So you would provide your own heat pumps that interconnect to the district loop. But you are saving on, cooling towers, you're saving on a boiler system, you're really simplifying what you have to purchase. And other models, kind of what we saw in Framingham, it could be some sort of utility agreement or some sort of private contractual agreement where the owner of the ambient loop pays for the system that interconnects in your building, and then you are paying for that through whatever utility contract you negotiate. So two models there, but I would say in terms of equipment on the building side, highly flexible, really doesn't change from kind of traditional approaches. You're just transitioning from from boilers on the heating side to heat pumps. Hopefully that answers the question. Yeah, so the Framingham model that we reviewed is probably the closest analog to that condition. And so there are affordable housing components that are going to be interconnected in that Framingham model. And so the real benefit to those particular building owners is that, one, under the current tax credit configuration, there really isn't an avenue for residential homeowners to access any type of tax credit or federal incentive. And so because Eversource, the utility in that case, is providing the infrastructure and also the building site equipment, they are able to monetize the tax credit. And the same thing would be true if it was a municipal owner, not a tax exempt owner installing that equipment. But because they're able to monetize that, they're able to get the savings associated with all of that equipment connected to the network, and then pass those savings on in terms of the utility rate to the homeowners. And so you're right, you wouldn't expect homeowners necessarily to be the ones that provide all of the building side equipment, especially in affordable housing applications. But I will say, in general, the equipment cost for a water source heat pump to interconnect to a district loop is going to be much more cost effective for a typical residential application than if that residential homeowner was going to have to also install their own wells. So you're eliminating, a significant portion of the upfront costs, and it really becomes very similar to conventional kind of split systems or a furnace, any new HVAC system at a residential scale. Yeah, Jemima? Yeah, so those are kind of generalities. The question was on the slide that was talking about $6 million for a 1,000-ton system of closed loop versus $2 million for a 1,000-ton open loop system. I mean, it's gonna change depending on the nuance of the system and the application. But typically, you're looking in like the 12 to maybe high end $18,000 per well on a closed loop system, especially once you get to that scale. Versus somewhere between 600 to 800, upwards of maybe $1 million per well for those open loop configurations. And so certainly those numbers would change depending on the size of the application, the actual specific equipment installed in those systems. But those kind of general costs for this region was what was used for that example. I think the key thing that's highlighting is that if you have the ability to use an in-well or aquifer-based system, there's tremendous land constraint saving or land use savings as well as potential cost savings, dollar per well in terms of capacity. Chad? Yeah, so that's a great question. And there's a lot of nuance in the design, but the more exciting new applications of thermal energy networks are a single pipe system. And so the way that works is essentially every building, if you just imagine them on a straight line, is interconnecting to the same pipe. And it's just one pipe. There's not a supply and return. The only way that works is if you have distributed ground source heat exchangers throughout that loop. Because otherwise, if buildings A, B, and C are all in heating mode, you're going to pull a lot of heat out of that system. And then once it gets to building D, they need to heat, but the water is too cold. And so you need supplemental and intermediate ground source heat exchangers to help temper that well field throughout the entire system, which can certainly be done. And especially in Cincinnati, where you have potentially this aquifer, you could do, rather than a single location of concentrated boards, you could have them distributed throughout the system. And the benefit of that is because you only have a single pipe, you're reducing your friction losses, you're drastically reducing pump energy, you're reducing the total infrastructure that you have to install. You don't have two pipes, you just have one. So everything in terms of like right of way and construction and implementation become much simpler. Hopefully does that answer that question? Okay, Ollie. Yeah. So we were musing about this earlier, actually. The potential of using the existing the abandoned subway tunnels or the existing subway tunnels under the city. It's a great question. I would say that the answer is maybe. I'm certainly not familiar enough with those tunnels and that network to understand exactly how it could be leveraged. But having a tunnel to route infrastructure through, whether that's just piping, potentially a place to do drilling that's not on the surface and disrupting traffic. Those are all things that could be considered and explored further. I couldn't say definitively whether or not that's a good solution or viable solution, but it's something worth exploring and considering. Could be cool. I don't know how we're doing on time. I guess we can stay. We can do a few more questions, but also I want to be mindful. I think we're over at this point. Are we good? No one's saying no. So I guess, Chad, you can fire away. Okay, great. Yeah. So the question is, are we looking at smaller scale district applications? And then from a pilot standpoint, how does load profile contribute to that? On the smaller applications in the study, we go into a little bit more detail. I think ideally, if there was going to be a pilot project, certainly there's room to scale this where it could even be a test well, then it could be a building conversion or a partial building conversion. But I think ideally it would be some small district component. And so potentially applications where you have one or two buildings, whether publicly owned or privately owned, that could be a part of that initial pilot phase to see how a district could scale from just one building to multiple would be really helpful. But really district energy networks can happen at any scale. So it could be a whole city, or it could be a few number of buildings, or universities. I think Ball State was discussed in the previous presentation. Miami University and Oxford has a district geo-exchange system for their campus. And so it can look like a lot of things and scale very differently. Certainly the mixed use and the impacts on balancing thermal loads is huge in terms of downsizing the system required. We were extremely cooling dominant because we're only doing commercial buildings that are, have more cooling loads annually than heating. That would, make your overall thermal balance unbalanced and drive you to a larger well field. But if you compare that with residential buildings where you're getting kind of a mix between weekday peak demand during the middle of the day versus evening hours for residential buildings and weekends, all of those things paired together help downsize the system. So definitely important. And one of the benefits, again, of a district system is that you do get that diversity of loads. Yeah, Fadi? Yeah, so in this particular study, again, very much so a screening analysis, so not a super deep dive that you would want to do as if you were actually sizing a district system of this nature. But in this case, it was using real utility data. So it is real existing energy use as the building is currently operating in existing conditions for the envelope, and then regressing that to climate data to understand how to then estimate energy use based on those existing conditions. So it wasn't using a regional benchmark or using any type of predicted performance. It was using actual utility data for this region and for our particular building stock. But yes, as you move into more detailed design, you would need to make assumptions around existing conditions and future conditions, building codes, all of that stuff. Okay, I think that we'll call it there. Thank you, everybody. Thank you, everybody, for staying the whole time. Appreciate it. And thank you.